Good day to everybody. Um, Let us know where you're tuning in from, and thanks for joining today's BioacousTalks. Do not let the cactus behind me fool you. I'm in a very cold and gray and snowy Ithaca office, and so greetings from Ithaca. And in the chat, let us know where you're tuning in from. Uh, our last presentation, we had folks from 51 countries. And even I think there was someone tuning in from Venus and also Mercury. So two additional planets as well to add to our tally. So it's super cool that we're all gathered here today to talk about um, bioacoust- bioacoustics. And um, yeah, today is especially cool because our speaker is someone who I've been lucky to cross paths with in the past month. We're about to collaborate together on a Hawaii Birdsong project. And I've just found with Mason, yeah, I guess innovative and creative ideas just spark all the time speaking with him. And that's in part because his work spans many areas from um, bioacoustics to animal behavior and communication. I saw that he was DJing at Lot Radio, which is a few blocks from my house, and that he also had um, a new installation about the Hawaii o'o. So as you can see from the speakers behind him, he works on sound installations to communicate and share about just the I don't know all that's amazing and all that can connect us with birdsong and more. So without further ado, I'm so grateful, Mason, that you have agreed to come on here and share about our work or your work, and we'll have time at the end for questions as well. So please, whatever this sparks while you're listening to Mason's work, let's make sure we can talk about it at the end. So thanks again so much, Mason, and the floor is yours.
Thank you so much for that very generous intro, Ben. I'm very happy to be here. Um, and just a quick heads up, I have a speech impediment that'll pop up throughout my talk. So today I'll be talking about my science and my art um, on complexity and efficiency in birdsong. So for the past 10 years or so, I've been really interested in this question of how and why birdsong, both biologically and culturally, evolves to be more complex. And in the past few years, I've expanded that work into an art practice that um, tries to communicate the importance of this complexity um, to, to the public. So yeah, I'll this talk will be split in half between the science and the art. So I'll open up introducing my work on complexity in bird song and other forms of animal communication. Um, and then I will close with an overview of the art I'm working on this topic. Um, so to start off, just a few words about what we mean when we talk about complexity in birdsong and in communication more broadly. So I think we all have intuitions about what makes birdsong more complex. Um, and, and those intuitions are largely are largely correct. So how hard songs are to sing, how hard they are to learn, and how much hierarchical structure they have. Those are the three main ways that people talk about complexity in birdsong. So these are the three main measures that people talk about. So syllable complexity is often talked about. Um, how many times the um, frequency trace changes in slope. Song complexity is often talked about as how much structure the songs actually have. This is, of course, a complex notion that we can talk about at the end if people are interested. Um, and then there's repertoire size, or how many types of sounds a species actually produces. Um, so these first two are often used as metrics to to compare complexity within bird species, whereas repertoire size is usually used across bird species. So there's huge variation in these metrics. Here is a great plot from a paper by Kate Snyder and Nicole Crianza that was published in 2019 that just shows the huge variation in syllable repertoire size um, across the tree of birds. Um, so from 2 to over 200. And the protagonist of this talk, the house finch, is right here. So here they estimate the house finch repertoire size at around 200, but as you'll see, our work on the East Coast house finches shows that it's actually much higher than that. Um, so after that quick introduction, let's talk about the house finch. The house finch is the species that I did my PhD on. It is an introduced songbird here in the New York area. Its native range is in California. Um, and just a cool historical note. Um, some of the some of the earliest papers about cultural evolution in birdsong were actually published on house finches in the 1970s by Paul Mundinger. He was a professor out at Queens College, which is actually where I did my work. So the lab I did grad school in inherited his amazing corpus of house finch recordings going back to the 70s. And I added to those around 2019. And there were also more songs from 2012 that other members of the lab collected. So in house finches, we have this amazing historical record of the cultural changes that have occurred in the New York area from about 20 years after the introduction of the house finch on the East Coast until now. Um, so house finch songs are fairly complex. So um, in general, birds know a- a- anywhere between one and seven song types that are composed of between 30 and 60 different syllable types. Shown here are the first 10 syllables of a house finch song from 1975 that Paul Mundinger recorded. Um, so I will play the audio of this song at its normal speed, and then I will slow it down so you can hear more of the detail. So as you can hear, there's a great amount of variation in their songs. And also just looking at the spectrogram alone, there are also some pretty clear types. Um, so what I, I did with these data is I had a big team of undergrads who helped to analyze all of these songs in Lusitania. Um, and then we identified syllable types by applying hierarchical clustering to the frequency traces. So these traces in blue are the data that we used to identify the types. Um, and that gave us about 500-ish types. Um, and then I used agent-based modeling to infer the processes that may um, have driven changes in the frequency of these types over time. Um, and I was most interested in the effect of the complexity of syllables. So how many times they change in their slope on the persistence of syllable types over time. Um, and this was motivated by previous work in house finches that shows that courtship songs are longer and more complex, and that males who sing longer songs at a faster rate are more attractive to female birds, um, and they have offspring earlier on in the spring. Um, and so the process of doing this, I built an agent-based model that I would be very happy to talk about more at the end of the talk. But this is a fairly standard agent-based model of cultural transmission, in which birds are born and they learn a set of types from a set of demonstrators, according to a set of biases. So it incorporates frequency bias, which is is conformity and anti-conformity, the attractiveness of the syllables themselves, based on their features, and the attractiveness of demonstrators. So maybe in house finches they have a preference for learning from males who are more red, for example. There's not a whole lot of evidence for that kind of bias in birds, but I included it in the model just because it's um, often incorporated in models of cultural transmission i- in in humans. Um, yeah, so I fit this model to the actual data using machine learning. And in short, I found evidence for a content bias for more complex syllables. So it seems that an agent-based model that assumes that birds have a preference for learning uh, more complex syllables does a decent job of reproducing the actual actual cultural changes that we observe from the late 70s, early 80s until now. And I've done some follow-up work um, in mourning warblers using a similar longitudinal data set um, that actually spans all of Canada. And we found the same thing. So we found evidence for a content bias that seems to be targeted towards more complex sounds. Um, so since I did this work, which at this point was about 4 or 5 years ago, I've been interested in looking at other measures of complexity as well that embrace innovations in AI and machine learning. There was recently a Nature paper that found that female zebra finches have preferences for males whose songs traverse more um, of the latent space in an embedding model. And I've been working on a method um, in catbirds, but I'm expanding it to other species as well, where I use a variation autoencoder applied to the individual spectrograms of sounds, and I construct an embedding space and then see how the average path length of songs in the embedding space, um, how that maps onto the different contexts in which birds sing. So here there's this song has 1, 2, 3, 4, 5 syllables that flow through the embedding space. So I take the average path length uh, um, as a function of the length of the song in syllables, and I compare that across different contexts. And we found that territorial songs, for example, are more complex than courtship songs in this particular species. So this is work I'm doing with our cornrike at Fordham, and it is in prep, and I'm hoping to apply it to other species soon. Okay, so moving on. Obviously, complex song is very hard to learn and produce, and there is a ceiling to how complex song can actually be, and that's because efficiency in singing is also extremely important. So when we talk about efficiency in animal communication, we think about it as as a ratio of the benefits uh, that the behaviors convey over the cost of producing them. And this idea is actually in idea that's borrowed from linguistics. So in the 40s, George Zipf, he came up with the idea of the principle of least effort, which is the idea that communication systems evolve to have a balance of functionality and efficiency. They need to be complex enough to convey the information as well as they can, while also being relatively cheap to produce. Um, so Zipf and others found a number of different patterns in language that are thought to reflect this trade-off. Um, Zipf's law of abbreviation, Zipf's rank frequency law, and Menzrath's law are like the three big linguistic laws that are thought to relate to efficiency. Um, and so a couple of years ago, after doing this work on complexity in birdsong, I was interested in whether or not this upwards pressure for complexity might be reflected in indicators of efficiency in their song as well. So I took the exact same corpus of song, and I looked for these five indicators of efficiency. So the first three are the three big linguistic laws, as I mentioned before. So Zipf's law of abbreviation and Menzrath's law and Zipf's rank frequency law. I'll first say that these first two, I think, have a very direct link to efficiency, but Zipf's rank frequency law is still quite mysterious and maybe even a little controversial depending on who you talk to. So I'll mainly focus on these two. So if you have a set of units, in this case syllables, and a set of aggregates, in this case songs, Zipf's law of abbreviation predicts that syllable types that are more common should be shorter in size than those that are more rare. So the average length of songs is shorter than would be expected at random. And then Menzrath's law predicts that songs that have more syllables in them should have shorter syllables in them, so that as song length increases in the number of units, the actual singing time increases at a slower rate than you would expect at random. And then Zipf's rank frequency law predicts um, that the relationship between the frequency of units and their frequency rank should be a power law. So these two, I think, have a very clear link, but this one does not. But I explored this one because it's often talked about. So a long story short, I found evidence for all three of these in Housefinch song. The fourth metric is that the transitions between syllable types has a small world structure where there is a high level of clustering, but a short path length. And this is what inspired the 6 degrees of separation idea, that you have a very a, a, a very large network that is highly clustered of humans around the world, but the actual path length in between a pair of people is often quite short. And so in language, this is thought to reflect the overall compressibility of a system. So systems that have a higher degree of small worldness are easier to compress in the learning process. Um, and so here's what a single syllable repertoire in a house finch male actually looks like, and this is what all of the sequences in the corpus look like. And if you compute a small worldness index, which is the ratio of clustering over the path length in comparison to a random network that has the exact same distribution of types. Um, the actual small worldness index is significantly higher than what is observed in pseudo-random sequences. Um, and then the fifth metric, so in language, words and sentences have a hierarchical structure that is a result of grammar. So as you can see here, sentences are composed of noun phrases and verb phrases, which are further broken down. And then the individual words themselves, so the phonemes in words are less hierarchical and are actually better described by a Markov chain. And so in language, we talk about sequences of phonemes having a Markovian structure at short distances and a hierarchical structure at long distances. And so if you compute the predictability in bits here on the y-axis as a function of the distance between sounds. So sounds that are adjacent to each other, sounds that have a gap of one, a gap of two, a gap of three. When you have a completely hierarchical grammar, you get a, a power law decay in predictability. A Markov model gives you an exponential decay, and then a composite model that has a language-like structure where it's Markovian at short distances and hierarchical at long distances. It's a combination of these two. So it's exponential up to a point and then is a power law. Um, and in language, you have this composite structure. So exponential at short distances and then power law at long distances. And the same thing is observed in house finch song. Um, so I should mention, of course, that in language, it's a lot easier to investigate these properties because we know what the actual relevant analysis units are. So we speak languages, which means we actually know what words and phonemes are. But when we are investigating these things in other species, we don't have this prior knowledge. So in this project, I actually replicated this whole analysis at 3 levels of granularity in syllable clustering. So I used hierarchical clustering, and so this level. So each of these individual lines is an appearance of a syllable, and then each of these colors corresponds to a type at 3 different levels of granularity in how we cut this tree. So like here, here, and here, for example. So the standard level of granularity that I've used and that others have used in house finches is this value of deep split of 3. which gives you around 600 types, and that's what I used for all of the results I just showed you. Uh, but if we overlump or oversplit all of the tokens into types, we end up with the exact same pattern. So these patterns are robust to assumptions of granularity in the types. So what I think is going on in house finches is that female preferences for more complex song have led males to evolve a learning bias for more complex song, and that because increased complexity is costly, that this has imposed pressure for increased efficiency and increased structure to make song easier to learn and produce. Um, so I suspect that these kinds of trade-offs are quite widespread. I recently did an um, analysis of Zipf's law of abbreviation and Minzrath's law across a large number of whale species. Here, I've only shown baleen whales, but I also included toothed whales. And I found that at least Minzrath's law is extremely widespread in cetacean communication. Um, uh, uh, but Zipf's law of abbreviation is only present in a small subset of species that already have Minzrath's law. And then I recently did a project in crows that showed that they express Minzrath's law and that the strength of it varies by age and sex of individuals, which is very interesting. And we're still trying to figure out exactly what is happening there. But Claudia Pasher and I are expanding this to a, a much larger number um, of crow species right now. So I should have more um, information about that soon. Um, so um, I guess moving away from the science and more towards the more subjective domain of art. um, Obviously, these patterns are very important for understanding the adaptive nature of communication in these species. But as bioacoustics nerds and animal communication nerds, I think we probably all agree that they're also uh, very beautiful in their own right, and that something is lost when these patterns degrade or disappear. Um, in this issue of animal cultures simplifying as populations decline is an issue that is starting to enter mainstream discourse, at least in the scientific community. There's this amazing opinion piece that was published in Science a couple of years ago that I highly recommend that everyone reads that kind of gives an overview of this issue. Um, but I think it is a particularly salient issue in songbirds because in a lot of songbirds you have songs that culturally evolve that are used in courtship. And so if a population crash leads to a crash in the complexity of song, that could have major downstream effects on population health. Um, so there are a few examples of this recently, like the North Island Kokako and the DuPont's Lark, where a population decline has led to a decrease in complexity in song. Um, but I think the most well-known one right now is in regent honey eaters in Australia, where it's reached a point where a lot of male honey eaters in the wild actually don't encounter very many other males as juveniles. And so they end up singing these very simple songs that often borrow syllables and elements from other species. Um, and so there's a huge effort right now being led by Ross Crates and others in Australia to see if there are ways um, to reintroduce more complex songs into captive regent honey eaters. But they are st struggling right now. And when I read this work, I was really inspired, and kind of I think that it's a very compelling story for kind of helping people to understand why animal culture matters. Um, and so, as I started to explore the idea of making art about this issue, um, I I came across this extremely famous recording that I imagine many of you have heard, uh, uh, of the Kauai a bird that went extinct in the late 80s. There's this extremely famous recording, a famous recording um, that lives in Cornell's Macaulay Library of the last male singing to a female that no longer exists. So the songs of the Kauai that we have access to are actually quite short and quite simple. They're often only 5 or 6 syllables in length. And over the course of extinction, it I think it's quite likely that the songs uh, b b became less complex over time. If you imagine a population decline here, in the 1820s, their songs may have looked like this. In the 1900s, they may have looked like this. And then the songs that are present in that last recording that we have may look like this. So I was very inspired to imagine these more complex songs. So how can we try to reconstruct what these songs may have looked like in the past, uh, based on what they look like now? Um, and I took a hybrid approach here. So art inspired by science. I found a mathematical model of the syrinx, the avian vocal organ, and um, I trained this model on the small number of syllables that we have access to actually be able to re reproduce them. Um, and by doing so, I can kind of map out the space that the birds may have been able to produce. And then I can randomly generate a bunch of new sounds from that space that, in theory, may have existed in the past. And then I can map out an embedding space. This is using Picanto, which I I think the creator Nilo gave one of these talks earlier this year. Um, and this gives me a bunch of theoretical types of sounds that I can then concatenate into imagined songs with a Markov model that is I trained on that last series of songs of the Kawai OO, which I then bring into art software. Um, and the result of this pipeline is a piece called Alakai 1777, which um, Alakai is the name of the swamp where the last male was recorded in the late 80s. And 1777 is the last year before European contact. Um, and this piece is a real-time agent-based model in spatial audio of the dawn chorus. So there's a real-time agent-based model that simulates birds interacting with one another in the canopy. And those interactions are translated into a spatial audio array, which you can see here in this image, but also behind me, actually. And the experience is a reconstruction of the uh, Dawn Chorus, which also includes a lot of archival recordings from Zeno Canto of other native birds. And over the course of the piece, it goes from realism into a more magical realism and incorporates other musical elements to kind of take things into a more um, abstract realm. So here's a small clip of this piece. So if you're interested, this piece is going to be shown in the New York area and also in Ohio in the coming months. So on the 20th, it's going to be shown at St. James Place in New York on the 22nd and the 23rd. It is at an arts festival at Flux Factory in Queens. And then on the 5th of December, it's being shown at Oberlin College if anyone um, is nearby. And then it's booked for a few more dates in 2026 that haven't been confirmed yet. But if folks are interested, I'll be announcing those on my website in the upcoming months. And I'm hoping to show this piece everywhere I can. So if you're interested in hosting it, uh, feel free to reach out. Um, so I'm doing this year-long incubator at the New Museum right now that culminates in an arts festival in mid-June of next year. And so over the coming months, I'm hoping to expand this piece into its final form. I'm hoping to actually travel to the exact location on Kauai, where that last mail was recorded, and get LiDAR scans of the forest, um, and collect spatial audio recordings of the dawn chorus to expand the piece into a multimedia realm and kind of have these artificial agents situated in the actual um, environment in which they lived. Um, and then yeah, I'm expanding my art practice as well. This is my first real piece I've made. Um, uh, but I'm also working on a performance piece with David Rothenberg, who I imagine many of you know, which will be shown here in Brooklyn in February. Um, and then I'm also working on an immersive sound installation with Alvaro Laiz, who's a photographer, um, about the about non-human experiences in the Amazon River Basin and beyond. So yeah, that concludes my talk, and I look forward to answering any questions that folks have.
Thank you so much, Mason, for sharing your work. And we have a few great questions that I've seen already. I will share the one that's in the Q&A, and then for folks that want to ask Mason any questions directly, please raise your hands and we'll pass you the mic. So Wendy is wondering, complexity in song changes between courtship and mating. Is there a mechanism through female choice to decrease the complexity? One would think the female would want a male that can teach a more complex song. Is it more, oh, like the male saying, this is what I can do, and therefore I'm a superior male when competing against another male, or something else?
Yeah, that's a great question, Wendy. And I think long story short, the like why complex song is adaptive is still very hotly debated. So there are a bunch of different hypotheses. Some people think that males who sing more complex songs are less likely to have experienced developmental difficulties when they were young. Others think that song is an honest indicator of other aspects of cognitive ability, there's a recent paper, I think in Nature or Science, that showed a correlation across different species between open-ended song learning um, and I think solving performance. And then some think that song is just a way of giving indirect information about the male's background. Like, is this male from um, my local area or not? And so having song that is more complex, you're able to encode more of that indirect information. So I'm not really sure which of those hypotheses I feel most strongly about. But I know it's an area uh, of big debate still.
Well, thanks. We have a few more questions in the chat now. So you've mentioned that juvenile males don't have as much contact with other males, or when they don't, they start borrowing signs from other species. And is there any evidence of similar occurrences in humans as well?
Yeah, that's a great question. I think the most obvious parallel is in language extinction. So there is a language extinction crisis happening all over the world right now, and a lot of effort is being put into um, trying to record those languages while they still exist. Mostly indigenous language that are indigenous languages that are produced in small scale societies. And a major driver of language loss um, is young people just being heavily exposed to other languages like English. And so a lot of the efforts to keep endangered languages alive are about increasing use among among young people, including on TikTok, actually. There are TikTok influencers for endangered languages now, which is really interesting.
Maybe Tyne and also Jeff and Fahad. Oh no, we answered Fahad's question. Tyne and Jeff, can I hand you the mic and you can ask your questions? I'll start with you, Jeff, of BioacousTalks regular.
Hey, can you hear me now? Sorry.
Yes, very well.
Yes, very well. Hey, thanks so much. This was awesome. I just wanted a question. Did I understand correctly from your Crow study that Menzies law showed variation across, I think you said sex, age, and maybe some other factors? And if so, I mean, my background's in linguistics, and so at the sentence word level, Menzies has a lot more variation, right, across languages and within languages. Whereas at the word syllable level, it's, fairly predictable. And so I've always been having this debate, what's a word, right? What's a word in animal communication? No one's really shown it, but at least this is some sort of descriptive model that you could say maybe those crows, there's some evidence here that we're talking about words broadly defined as opposed to syllables. And I just wanted to see if you had thoughts on that.
Yeah, that's a great question. So I interpret in both the house finches and the crows, I interpret the analysis as being more analogous to um, words in sentences than phonemes and words. And that is because I'm looking at how the length of a continuous sound changes in a sequence of sounds separated by silence in both the house finches and the crows. So I think that's a part of the driver of that variation.
Thank you.
Cool, thanks. And now we will pass the mic to Tyne.
Yeah, sure. So this is really awesome work. And I had a bunch of questions, but you kept answering them as you went along. And a million years ago, I did a little bit of work on song sparrows where we found that there was a difference between the young first year males and the older males, and that the older males had a more local sound, and we weren't really able to study any sort of directionality there. So I was wondering, I know you're really early on with your crow stuff. Um, are you seeing any sort of directionality to the complexity over the ages? Where are they like learning with age, or are they sort of pruning out? I mean, by the graph you had there, I would expect that they're learning with age more based on the call duration.
Yeah, I think so. So it is still very early on, but the pattern that we're seeing is that, which is the opposite of what I expected, is that the efficiency of call sequences actually decreases with age. So I expected uh, that the young birds would produce less efficient sequences, and that it would improve with age. But what it may be is that in the juvenile birds, their sequences are efficient because they are basically producing sounds within physiological constraints that have evolved for efficiency. And then as they learn sounds, and the sequences become more complex, you get that trade-off where more complex sequences then also become less efficient. That's my hypothesis right now, but it is very early on.
Great. That's fantastic. Thank you so much for sharing both your science and your art. That's an amazing
Thank you.
installation you've created.
Thanks,
Thank
Tyne.
you.
Where are you tuning in from?
I'm coming from Calgary, Alberta, in
Oh,
Canada.
cool. Um, I like your pseudonym, Avian Eco.
That's the
Um,
name of my business. Yeah.
oh, excellent. I'll check it out. Next, we can pass it to Eric.
Hi, Mason. Thanks for the talk. This was really fascinating. I was just curious if you know of any studies that show song complexity increasing as populations recover. I was thinking in particular of humpback whales because their populations have been in recovery for some time now. But I just wondered if that was a phenomenon that, like, is there a lag between recovering complexity in song, or is it pretty immediate?
Yeah, that's a great question. I don't think I don't know of any studies like that off of the top of my head, but I know that there are studies that show that after new humpback whale songs are um, invented, as they are transmitted between populations, they increase in complexity, I think. I think that's the pattern. Um, but there is one example. So, in the North Pacific right whale was pushed to the edge of extinction, and all of the acoustic data that we had on them for a very long time was from those populations that were at the edge of extinction. And so, as they have recovered, it was actually the first paper demonstrating that they produce songs was published just a few years ago. And so I think that may be an example, um, and a very optimistic example as well.
Awesome. Thank you. I'll have to look that up. That sounds great.
Yeah, I know there's active work with the alala in Hawaii, the Hawaiian crow, where they're doing these acoustic enrichment treatments to try and um, teach the alala in captivity some of the alarm calls that they've since lost after being captively bred. And I think at this point they're able to recognize these alarm calls as signs of an, a near and present threat. But the last I had learned, they still were not able to actually produce them themselves. And so that's one example of trying to teach a population. I mean, at the very early stages of recovery, they haven't even been reintroduced yet. But yeah, trying to teach them some of the syllables and sound types that they'd since lost. So I think we've got one or two more questions. And next we'll pass it to Arul. So you've got the mic now.
Hi Mason. Great talk, by the way. I just wanted to talk a little about the the time where you mentioned about reconstructing lost songs, and I was wondering if we can use that same method to sort of figure out the vocal repertoires of of some of the obscure species for which we do not have a lot of data on the libraries. So could we use their seedings metrics and then figure out their vocal repertoire or something like that? I just want to learn more about the method in general to reconstruct the lost songs.
Yeah. So I've gone back and forth on this. Um, uh, because I'm using this pipeline for imagined songs in an artistic context, and I am very interested in whether or not it could be used in a real context. Um, like I've been interested in, for example, if I used this pipeline on Regent Honey Eater songs, and then we did a playback experiment with captive birds, if they would respond to those reconstructed songs, um, as if they were from other Regent Honey Eaters. And honestly, I'm not sure. I think one way of testing whether or not it could work, which would actually be fairly straightforward, would be to run the pipeline on a small subset of songs for a species that has a lot of data, and then see if the output approximates the other data. Um, but yeah, if you're interested in in more details about that, just feel free to email me. I would love to
All
talk
right,
about it.
yeah, I'll probably write to you soon about it. Thank you.
Awesome. Mhm.
Does anybody else have any questions for Mason before we pack up? Willow, I will pass you the mic.
Thank you. Thank you so much, Mason, for the talk. That was fantastic, and your visualizations are quite beautiful. I just had a quick question. So in plants, there's this sort of genetic memory that we find. For instance, like seeds will carry traits through generations. One example that comes to mind is maybe a plant is in a region where they start to become attacked by a certain insect, and they'll develop these chemicals that are used to ward off or communicate to those insects. And maybe it's a lot of predation from these insects in one area, so that trait will actually be passed down to that chemical type of communication, if you will be passed down to the future generations through seed. And it's sort of like a plant culture, if you will, carried through genetic memory, not direct learning or teaching from parents or the surrounding community. And it's how we get land races, or for instance, extreme localized diversity in plant fungal preferences. Um, I was curious, is there any evidence for this type of genetic memory in animal species?
Yeah, definitely. So I think that you could refer to kind of any form of genetic inheritance as a form of genetic memory. In a way, like DNA holds the history of a population. But then there's also epigenetic inheritance, which I think is more analogous to the process that you're talking about in plants. Um, Changes in the expression of genes in one generation uh, could be passed on. Um, and then, of course, in a lot of animal species, there is culture. So there is a lot of memory of migration paths, of tool use traditions, etc., that um, are culturally passed on in species. So yeah, I think there are a lot of analogous things happening.
May I add a quick follow-up to that?
Yeah, sure.
So I guess this is where I'm kind of interested. So I know migration patterns, for instance, is one that is commonly passed down through genes, basically, because they don't, for we think of turtles. But do you know if there's any examples of actual tool use or that type of culture that's passed down through genes? For instance, maybe a bird uses a particular type of tool and they have offspring, but their offspring, maybe the parent dies and the offspring are kind of isolated, or maybe they're taken out of that environment. Will they still kind of just instinctually know how to create those tools?
Yes, I think there are some examples in ants, but don't quote me on that. Also, um, is it the palm cockatoo that they construct, uh, they make drumsticks and they make rhythms on trees as a part of their courtship display. And I would suspect that the construction of the drumsticks is maybe genetically inherited, but then the preferences for different rhythms is cultural. But that's also uh, that's just a hypothesis.
Thank you.
Mhm.
Thank you, Willow. And many thanks again to Mason for joining us. I expect that we will meet a few more times before the holidays, so stay tuned for invitations. And until next time, I hope that we have some great upcoming talks at the intersection of bioacoustics, art, conservation, and all that inspires us. So have a great rest of the day, and see you next time. Okay.
Thank you so much for having me.
Thanks, Mason. Bye, everyone.